Afternoon, everyone, and thank you so much for joining us, the latest in our series of online seminars. The subject is, as James mentioned, specifying glass, but from the perspective of considering circularity, performance, practicalities around the subject of low carbon glass also. So in partnership with City Press, we commissioned census-wide the research consultants to undertake a survey just to gauge the level of awareness and understanding of low carbon and circular glass when specifying glass for projects. This is a survey that was carried out very recently. In fact, the 13th to the 17th of March, we surveyed 100 UK-based architects and specifiers who have influence or responsibility in the specification of glass for projects. Some of the key findings of this will be presented within the webinar. So to set the scene, 37% of global CO2 emissions come from buildings and the construction industry. The drive towards a sustainable built environment has seen a significant growth in commitment from architects, developers, contractors, etc., to find ways to reduce the carbon footprint of buildings. So building owners, developers, tenants, they're all increasingly looking for ways to showcase their commitments to sustainability. So this has led to a far greater understanding of how carbon is used throughout a building's life cycle. So the whole life cycle carbon of a building project. From the embodied carbon of extraction of virgin raw materials that will be used in manufacturing, through transportation, the building's use, its repair, replacement, all the way to deconstruction or demolition, and even through to the potential for reuse under circularity. While embodied carbon occupies the vast majority of these life cycle stages, the life cycle stages we see on the illustration on your screen, historically operational carbon, or the energy use, while only occupying stages B6 and B7, would have had a higher overall carbon weight when looking at the overall project's life cycle. Before we dive deeper into low carbon glass manufacturing, let's have a look at the history and look at how effective glass design has been in reducing operational carbon in the area. In this area where glazing manufacturers and technology experts, well, they've been making significant strides for decades. If we go back to the 1970s, the energy crisis, we saw a challenge that sparked a major shift in the glazing industry. At that time, rising energy costs pushed homeowners to find ways to reduce their heating bills. And one of the key solutions adopted at that time was double glazing technology. So by choosing glazing with better insulating properties, people were able to cut down on their heat loss in their buildings, and ultimately they're improving the energy efficiency of buildings. Albeit at that time they weren't doing so because of sustainability. Really, they were doing so to keep costs down. This was one of the earliest steps towards reducing the operational carbon footprint of a building through a smart glass design, but it set the stage for further innovations in energy efficient glazing. So over the years in this area, definitely influenced by legislation like the introduction of energy performance certificates in England and Wales in 2007, improvements to approved document L around insulation and lower U values. This is where design and manufacturing first worked to make advancements. Consequently, this is also where historically as a designer or a specifier, the choices you would make with regards to your glass spec would make an impact. As we move forward, we can see the adoption of project energy statements and even sustainability reports. An energy statement outlines how a development meets local energy efficiency standards. They're required for most planning applications and calculates predicted energy use and CO2 emissions while detailing also strategies to reduce them. It's now necessary in many regions, even within non-dwelling projects, proposals to demonstrate being lean, being clean, being green. The first one of these, being lean, is to use less energy in the building. And this would definitely be influenced by your glass design. So for example, through the use of an appropriate glazing spec, like maybe applying a solar control coating to the glass, I can meet the energy statement's target for the project. I can provide the correct amount of insulation and reduce solar heat gain. In turn, this will reduce the requirement for air conditioning on a project and heating. The most frequently used glass technology within insulated glass units really is glass coating types. So in modern high performance IGUs, the two most frequently used, most popular would be low E coatings and also solar control coatings. So low E coatings' main function really is to reflect long wave radiation or heat back into the space. Will often be used in residential projects. For high performance and for low U values, an offline coated low E product should be used, such as Pilkington Optitherm S1, which will arrive at a 1.0 center pane U value, for example. Low E coatings, it's worth pointing out, are designed to intentionally allow a degree of passive heat gain into the space. So they therefore will be used in passive house projects. Solar control glass coatings, they'll insulate just as well or better than low E coatings. And in addition, they will control the amount of heat buildup through the solar heat gain. This is obviously particularly important in projects where you have a large expanse of glass, where there's a reliance on HVAC air conditioning, and that's looking to be reduced, where human comfort is a factor. Standards watch here, BSEN 410 for glass in buildings is the determination of luminous and solar characteristics of glazing, and this specifies methods for determining the light and solar energy characteristics of glazing that's used in buildings, including the visible light transmittance, the reflectance, and the solar heat gain. And BSEN 673 is thermal transmittance of glazing. So that standard specifies a calculation method to determine the thermal transmittance of glass. So for optimum performance in commercial buildings, solar controlled glass is used. Pilkington have a product called SunCool, a collection of coatings which are recommended. Key to choosing the correct solar control glass is understanding what your project target G value is. Once this is known, that's almost the anchoring point. Once this is known, we can review the most suitable coating and then understand its appearance. Even at a glance, before samples are examined, you can have a look at its appearance through photometric data. So something like light transmission, reflectance values can be looked at, reviewed, just to get a sense of how tinted the glass will appear. So we've talked about how to treat the glass to make it perform much better in terms of reducing the operational energy consumption in buildings. But what about optimizing your window design, the apertures, the configurations, to minimize waste? So when specifying glass, it's also key to understand how best to use the material from a dimensional perspective, just to limit the amount of waste. Our largest panels that we produce are called jumbo sheets. They're about 6 meters by 3.2 meters. We sell those on to glass processors who produce double glazed units, etc. from. And I asked one of them to share some optimized IGU panel sizes versus some examples of very poor IGU panel sizes. So based on one of these jumbo sheets and factoring in edge deletion, etc., the best optimized IGU panel size would be about 1.48 meters by 3 meters. With those dimensions, you can get 4 panels from one jumbo sheet. That's only 8% waste, so it's a really good balance of efficiency and sustainability. An example of a poor IGU design, and there's not really much in them, really, but there's in terms of their dimensions, etc. But there's a massive difference in terms of their efficiency from a jumbo sheet. So this example, 1.65 meters by 3.3 meters, you'd only get 1 panel per jumbo sheet. So that's a huge waste, 72% waste, lots of material loss, and an increased cost. So you will, the end user pays for it, really. So that's quite a good handy design guide, I would say, to take note of in today's seminar. So Glass for Europe have published findings on the subject of energy conservation in buildings. European buildings emit around 760 million tons of CO2 per year. And if all the buildings in Europe were equipped with high performance glazing, in 2030, 94 million tons of CO2 could have been saved annually, which is the equivalent of a reduction of about 28% in buildings. And the 2050 data shows that 69 million tons, or 37% of CO2 emissions from buildings, could be avoided due to or through using high performance glazing. So as buildings become more thermally efficient, so as people adopt the use of this better insulating glass, for example, or glass which reduces heat gain, and other materials also become much more thermally efficient, and also we see an increase in power being provided by renewable electricity. So operational energy itself decreases, and then for embodied carbon is making up a growing share of the overall environmental impact of a building now. So this now leads us on to the concept of low carbon glass. And when we talk about low carbon, in this context, we're not referring to the high performance glazing we just discussed, the glazing that improves the building's operational efficiency. Instead, low carbon glass specifically refers to glass that has been manufactured with a lower embodied carbon footprint. So in other words, it's about reducing the emissions generated during the production process from the raw materials and all the way through to the final product. So let's first look at the embodied carbon of conventional standard float glass. Fossil fuel, I have a graph in the center there, the donut-shaped graph. On the left-hand side, you can probably see fossil fuel combustion, but it's significant at 42%. And that's mainly because a float glass furnace, the temperature is required to reach up to 1,600 degrees to melt the batch materials, the sand, etc. We can also see here areas that can be effective by increased recycled content in the raw material manufacture, and also an area in electrical consumption, areas that we can look at improving to produce a lower carbon glass. So we have some survey insight from the survey we ran last week. In question 1, we asked participants, how often do attendees specify low carbon glass today? 66% said frequently, 23% occasionally, and 11% sometimes, which means percentage translates to 53% of projects. However, I'm not sure how informed the participants were on what we define low carbon glasses as, because low carbon glass as a product has really only been made available by ourselves and our competitors over the recent years. It's still something of a niche that is growing, I would say. I look now into alternative fuel use to fire the furnace, that furnace that reaches 1,600 degrees. So something groundbreaking in flow gas production took place back in 2021 with Pilkington, and our first hydrogen fuel trial. In fact, it was the world's first at the time, using hydrogen to fire a glass furnace. It marked a big step in reducing the carbon footprint of the production. As they increased the hydrogen content into the furnace, they also noticed changes in the flame appearance, which is a key part of understanding how hydrogen interacts with the float glass process. I suppose the best part was that we achieved a 7% reduction in overall CO2 footprint at the time of producing this glass for a trial. It might sound small, but it's a big milestone, especially since it's the first time hydrogen has ever been used in float glass production, and it's something that we've earmarked to expand on in the future. So at this point, it really was a proof of concept trial, but it helps us to plan into the future, knowing that we can access and use hydrogen. 2 very big hydrogen projects are underway for our UK operations, and they're both pretty exciting. So the first one is the HyNet pipeline project. This is all about supplying blue hydrogen through the HyNet pipeline. Right now, it's planned to cover 40% of our glass float plant in St. Helens energy needs. Eventually, it could hit 100% of the energy we need to fire the furnace. Phase 1 will see hydrogen production plant HPP1 supplies Staniflow Refinery and Encirc, who are a glass container maker near us. And then phase 2 will expand the supply of the wider HyNet network. So that will also then at that point include Pilkington's float plant in St. Helens. Some of the key players in this are EET Hydrogen for production, Cadnet for the pipeline, and Innovin for the hydrogen storage. The second project underway is on your right-hand side. Again, this is at Greengate itself. So HyNet is a big network that we are going to be plugged into, but the Greenian project takes place on Greengate, our float line, where green hydrogen will be made using renewable electricity. And this will only power one port at our furnace, but because renewables can be inconsistent, the supply will vary a bit. It's been run by Greenian Hydrogen. So both projects are relying on third-party funding with lots of support from the UK government, who've reviewing at the moment Hydrogen Allocation Round 2, HAR2. Pilkington's role will be integrating hydrogen into its operations, and as I've explained, we've already tested that process. The costs are expected to be similar for the hydrogen as they are for natural gas. Natural gas is what we currently use to fire the furnace. So in short, both of these projects are a big step towards a greener future. So here's another exciting milestone that took place in February 2022. And this was, again, another world first. It was 100% alternative fuel float glass production. So with the earlier hydrogen trial, we didn't fire the entire furnace with hydrogen, but in this one we were able to 100% alternative fuel float glass production, and it made a huge step towards making our glass production more sustainable. It was done using alternative fuels, and then it led to a 40% reduction in the overall CO2 footprint of the glass that would have been produced during this campaign. So it's a big win for low carbon glass manufacturing. And it shows just how much we can cut emissions with the right energy sources when they're available. Pilkington have used renewable biofuel, diverting end-of-life waste such as from cooking oils, etc., from landfill. Big efforts are being made to use more renewable electricity instead of fossil fuels in the glass production process. Starting in 2025, there are 3 major projects going on to increase electrical melting to the highest level ever within the NSG group globally. So this will be supported by the German government, and the goal is to gradually roll this system out to other float lines by 2030. They've already working on a global roadmap to make this happen. So it's another big step towards a cleaner, more sustainable glass production process. This won't affect Greengate or St. Helens float line. Obviously, we're pursuing the hydrogen, etc., but still interesting all the same. So we recently ran a trial to assess how solvent in carbon capture technology behaves when applied directly to our waste gas stream. To support this, we installed a CCSCU, so that's a carbon capture solvent compatibility unit at UK5, the St. Helens float plant. This trial will help us understand how effective this technology can be in capturing carbon from our operations. And in the future, as we move into hydrogen, the carbon will be reducing anyway from our operations, but it certainly is something we will continue to work on and explore. So more survey insights this time. For question 3 in our survey: what prevents wider adoption of low carbon glass? We can see at the top of the list there, 42%. Well, it's concerns about performance and durability. 42% of people answering the survey mentioned this point. But if I can put your mind at ease, the production of our low carbon glass, and I'll step you through that later on, really it is all about how the furnace is fueled, etc. The glass itself is exactly the same as our standard float glass, exact same density, etc., appearance and workability. So that really shouldn't be an issue when people learn more about low carbon glass. So circularity in glass. What is circular glass? Well, glass, as you probably know, as a material, it's infinitely recyclable. And our definition of what circular glass is using post-consumer cullet or waste glass, waste flat architectural glass, and recycling that into more float glass. And what we really look for with circular glass is post-consumer. So what we're really looking for here is end-of-life building glass to be able to to source donor projects where there's glass, and it can be collected, it can be cleaned and sorted through glass recycling and then delivered to us as cullet. We then reintroduce that into our production. So cullet is an old term used in glass manufacturing. Cullet is essentially what you can see in your picture there. It's the waste glass that's collected and turned into small little granular bits of glass to be reintroduced back into our float line. It's considered the glass maker's most valuable raw material because it replaces virgin raw materials. Where you have cullet, you don't need the sand, etc., or as much of the sand. It melts at a lower temperature than virgin materials, so as it's already glass, it doesn't take as long for it to melt into molten glass as it takes the primary materials of sand, etc. The temperature that they need to, and the amount of time in the furnace they need to turn into molten glass is obviously longer. So that reflects in a lower strain on the furnace, essentially. It doesn't decompose to emit carbon as it burns off, so it melts, but because it's already, the batch materials have already emitted their carbon, burned that off the first time they were melted. Cullet doesn't do so when it is being remelted back into molten glass. 10% cullet can reduce 3% fuel on the furnace. So it has a huge part to play, not just in recycling a material, but also bringing the temperature and therefore the embodied carbon of the production down. And of course, it diverts waste from landfill. While some architectural glass is collected and downcycled, the majority of architectural glass does end up in landfill, I'm afraid. And also, we're reducing air emissions. As I mentioned, doesn't decompose or emit carbon. So there are three main types of cullet. There's our own internal, so that's what we refer to as line return. So if you've ever seen a float line in operation, it runs continuously, and you've got a long ribbon of glass that is cut into those jumbo sheets. But all the way along the edges, you have selvage, which is trimmed from the edges. That's all collected, becomes cullet. And then we have our breakages from the warehouse, etc. So they always have been traditionally collected and reintroduced into production because of their benefits. And that's happened well before sustainability was even considered, really. The next type we have is pre-consumer. So this is cullet that has been produced from downstream operations. So our customers, glass unit makers, people who buy large sheets of Pilkington glass, manufacture double glaze units, etc., from, will have a certain amount of waste. They will have breakages, etc. And we have provided them with these very safe mobile cullet bins where they will safely deposit the edge cuttings of their glass, store them, and then when we come to deliver glass, we will collect that cullet and bring it back to St. Helens to be washed and turned into more cullet for our production. Now, the third type is post-consumer. So this is end-of-life glass. This is glass from windows, doors, curtain walling. Very much seen as a large untapped resource. Otherwise, it's been sent to landfill, or as I mentioned, it might be downcycled into aggregates. So we're very much encouraging people on projects, renovations, etc., where they have a good amount of glass for it to be dismantled, and we can assist in it being collected, cleaned, recycled into more flat glass. So this is the closed loop recycling that we're encouraging. A great example of this is our initiative. So we have a Renew Glass initiative, and this program promotes the recycling of waste glass back into the more float glass. to close the loop, and provide a more sustainable circle. We have guidance on this that we can issue, but essentially you'll see in that picture the circle from production, from a building that's signposted for demolition. It's key that the glass is segregated. It can't be mixed in with other waste materials, etc. So it's more thinking around the deconstruction and the demolition phase, really, to collect it, adequately segregated. And then with our partners, it'll be cleaned and sorted and sold back to Pilkington, essentially as cullet, which we will use in our glass manufacturing. So what type of glass can and can't be recycled, I hear you say, because obviously we can't take everything. It's very important to understand what's in situ, but you'd be glad to hear that actually most types of glass can be recycled. So float glass, textured or patterned glass, toughened glass, coated glass, as I mentioned before. Those coatings, the solar control coatings and OE coatings, are microscopic, so they pose no issues at all. And various types, laminated glass, printed glass, they can all be recycled as well in certain ratios. The types of glass that are problematic that we don't accept, wired glass, so that's like Georgian wired glass, because of its metal content. You see here insulated glass units. That means that a full insulated glass unit with its spacer bar and sealants can't be put into our furnace directly. They need to be separated out. So the recycling process before it comes to St. Helens, DGUs are dismantled in such a way as the perimeter is removed, but 80% of that glass will be saved and can be used, crushed and used as cullet. It's very important that metal and trash, so this is really to encourage people on site to have a very well labelled skip, where it's very clear to anyone on that site that they can't be putting in Coke cans or various things in to contaminate the glass. In question 8 and 9, we asked how important is circularity today, and will it increase in influence? So 80% feel that circularity is very important today, and 74% feel that there will be a great increase in the need for circularity, and I think that's something that we are seeing, where people are looking to detail their design for dismantling, understand what they're specifying, and asking the question, will it be problematic for recycling in 20 or 30 years' time? So I definitely think people are much more considerate on the subject of circularity in their design. They're not just designing for that building's life, they're thinking about going past that. So low carbon glass, obviously I've explained all the ingredients that go together to producing low carbon glass. Pilkington launched our own low carbon glass, Mirai, back in October 2023. So Pilkington Mirai has 52% less embodied carbon compared to our standard float glass. In terms of the low carbon glass types on the market, it certainly is the best performing around the reduction of embodied carbon. It has a GWP, a global warming potential, of less than 5 kilograms of CO2 per meter squared. And this is achieved using a combination of 100% alternative fuel to fire the furnace when we are running the Mirai campaign. High recycled glass content, so we'd have 50% cullet used in our batch mix. A typical batch mix for standard float glass probably has somewhere between 15 to 25% cullet use. So we always use cullet, but when we're running the Mirai campaign, we use more. So we use, and that's where we need more of the glass, external glass. So the glass from our unit makers, that pre-consumer, and also, of course, the post-consumer. So the glass, the end-of-life glass from buildings. As I mentioned earlier on, this is just the way the glass is manufactured. The glass itself is exactly the same aesthetics. There's no impact on the transmission, the clarity, the quality of the glass. So it can be coated with solar control coatings and coatings, all the coatings necessarily. It can be laminated, etc. So you can work with it in exactly the same way. And yeah, manufactured in accordance with EN 752, which is basic soda lime silicate glass production standard. So future trends and regulation, what's next? Well, in terms of policy and also industry standards, the government position as of March 2025, the UK government hasn't set rules requiring builders to measure or reduce embodied carbon, the WLC, in their materials. However, there's progress. The UK now has its first industry-wide net zero carbon building standard. While it's voluntary, it definitely gives clear guidance on cutting emission from both building operations and the materials themselves. So it's helping the industry move towards more sustainable construction. Industry trends, the construction industry is pushing for whole life carbon to be factored into building regs, recognizing the need for more sustainable practices and lower carbon emissions throughout the building's life. At the same time, major engineering firms are already carrying out WLC assessments on all their projects. They're using more low carbon materials like mass timber, which locks in carbon instead of releasing it like traditional cement. There's also a growing focus on choosing durable products and reusing materials wherever possible to cut waste and to reduce the environmental impact. So that comes back to that point I made about efficient when you're designing your apertures. Consider maybe, how you can tweak those openings so that they fall into a certain dimension that is more forgiving in terms of the waste. Environmental product declarations, or EPDs, are now essential for showing environmental impact of materials, including their carbon footprint. More and more companies obviously require them and are pushing for greater transparency in how they're put together and in the supply chain. You can download all the Pilkington EPDs from our website, and we also place GWP figures in our spectrum calculations for easier access. I'd also like to signpost some excellent guidance material that's available from the CWCT. These give advice on understanding EPDs, know what you're looking at, and also very influential is a methodology on how to calculate the embodied carbon of facades. So these documents are very influential with good reason, very informative. So to wrap things up, here are the key takeaways. So circularity and low carbon glass are becoming increasingly important, but there are still some challenges up the road. The pace of progress will really depend on factors like regulatory framework, costs, advancements in the supply chain, making it easier to, for example, collect end-of-life waste glass. But looking to the future, we can expect to see more recycled glass being used, along with the rise of smarter glass technology that will make buildings more energy efficient and sustainable.